Welcome back, everybody, to video 2 of our 4th unit on neural networks. So now that we have a basic understanding of neural networks in general, we're going to dive into more detail on the perceptron, which is the basic processing unit. So let's get started. So the perceptron is a unit with weighted inputs that produces a binary output based on a threshold. So this is exactly what a neuron does in an artificial neural network. And as a result, a neuron is just a generalization of the perceptron. So perceptrons were conceived of first, and then they were actually applied in neural networks. So these are simple processing units, receives an input, produces a binary output based on a threshold. So neurons don't always have to produce binary outputs. However, that is how perceptrons started. So we're going to talk about them as a simple case, simple explanation type scenario, and then we can talk about how using a different thresholding function is going to be able to change the type of output that we produce. For example, in a regression task, we don't want a binary output, so we're going to have a different threshold there. So the basic elements of a perceptron is that it has inputs that may come from the environment, or they could even be outputs of other perceptrons. So when we have multiple layers, the inputs that we are receiving in the second or greater layer are going to actually be the outputs of the first layer of perceptrons. So again, we have the bias unit as well. And then each of these is associated with a connection weight or a synaptic weight. This can be thought of as the strength of connection. Inputs with a larger associated weight will have a larger impact on the output. So each input receives an associated weight. And then in the simplest case, the output Y is the weighted sum of the inputs. So these are simply the inputs multiplied by their weights and then summed together. Again, we have our bias unit here. And then our bias weight would be the W naught, X naught being the actual bias unit. Typically, in fact, in almost all cases, this is just a positive 1. The W naught in a simple case would be the intercept value, and it helps make the model more general. So we don't want the inputs to be the only part of our output, because then our network wouldn't be able to account for noise and wouldn't be able to generalize to new instances. So remember, in previous units we talked about the ability to classify new information correctly as what's ultimately important. And so the bias unit is going to help us do that so that we can do more than accurately classify the training data, but we can apply a network to a validation test set as well, and it will still do fairly well. And that is called generalization. So these are the basic elements, and let's dive into a little bit more detail. So in learning, what we're really doing is with given weights W for an input X, we're going to compute the output Y. And to implement a given task, we need to learn the weights W, which are the parameters of the system, such that the correct outputs are generated given the inputs. So it's fairly simple. That's all we're trying to do. When we only have one dimension and X is fed from the environment through an input unit, all we're going to have is Y equals WX plus W naught. So we're actually going to have a linear fit where W is the slope and W naught is the intercept. So with only one input, we have a line, and the output can be used to implement a linear fit. But with more than one input, the line becomes a hyperplane. And so now the perceptron with more than one input can be used to implement a multivariate linear fit. So all we're doing is adjusting these weights. And the weights or parameters, same thing, adjusting the weights so that we get the output that we want to. So not too difficult, but we can start applying threshold functions, or sometimes you're going to hear these as called activation functions. So the perceptron defines a hyperplane, and as such, it can be used to divide the input space into two: the half space where it is positive, and the half space where it is negative. By using it to implement a linear discriminant function, the perceptron can separate two classes by checking the sign of the output using an activation function. So in the simplest case, this activation function or threshold function is a simple step function. The output value is 1 if the perceptron exceeds a certain threshold. In this equation, A is our threshold, and so 0 is the value of that threshold. So anything greater than that in our output is going to get a value of 1, and otherwise a value of 0. So then after we have that binary output, we can choose our first class if it's a 1 and our second class if it's a 0. So this is a simple binary classification. However, that is not often used. More typically, we have nonlinear transformations. And to do that, we're going to use the sigmoid threshold function. There are other threshold functions, such as the hyperbolic tangent. However, they generally, in principle, work exactly like this. They would just be normalized to different values. So the step function is replaced by a smoother threshold function, the sigmoid, so that we can do a nonlinear statistical modeling, and then ultimately it can be used to calculate gradient descent. So this is the important part of using the sigmoid, is that it's continuous, it's smooth, and we can calculate the derivatives of this function. Here's a graphical representation of that. So you see it in general is a lot like the step function. Nu is our parameter here in this graph, and it can go from 1, which would just be the red curve, to 1/2 the blue curve, and make it a lot more gradual, to a value of 10 in our purple curve, which essentially is a step function at this point. However, this function is differentiable, so it can be used in a lot more situations than a step function would be. A neural network can be thought of as a nonlinear generalization of the linear model, both for regression and classification. In other scenarios, you might also hear of the softmax function, which is very similar to the sigmoid function. The sigmoid function is used for the two-class logistic regression, whereas the softmax function is going to be used for the multi-class logistic regression tests. So softmax might come up a couple times, but in general, just knowing the sigmoid is going to help you understand the concepts in its entirety. So this is the common threshold function, the sigmoid, also known as an activation function, and it's going to take our summation of outputs, or summation of inputs times weights, and then classify it as a 1 if it reaches a certain threshold and 0 otherwise, while being differentiable. So in parallel, perceptrons actually gain their power. K-parallel perceptrons here, with the inputs and outputs, are going to each have individual weight vectors. So now we don't just have one weight vector, we actually have one for each output. And so these are going to be summed a little bit differently. In the bottom you see this formula written in matrix notation, where we're actually taking the transpose of the weights multiplied by our inputs to produce our outputs. So the entire class of weights are going to go into producing our entire class of outputs, y. So each output is a weighted sum of the inputs, just like before, but when there are greater than 2 outputs, we need multiple perceptrons to process them. So each of which is going to have a weight vector. When used for K-class classification problems, there is a post-processing to choose the maximum, typically a softmax, if we need to calculate posterior probabilities, how confident we are in our classification, or actually perform the gradient descent, which is going to be used in the learning stage to calculate derivatives and actually choose in which way do we adjust the parameters of our model so that we can produce the correct output. So in parallel, perceptrons gain their power. Each perceptron has a weight vector, and those are all used to produce our output. So in summary, a perceptron, or a neuron in the generalized case, is the basic processing unit of neural networks. And then as well, a perceptron is a unit with weighted inputs that produces an output based on post-processing or a threshold function. So pretty simple by itself. However, we're going to see when they're combined into a network, it gets a little bit more complicated. In our next video, we're going to talk about backpropagation, which is how do we actually apply gradient descent to train these networks? How do we actually adjust the weights and the parameters to produce the desired output? But we will dive into those details next time. So thanks for listening to this short video. Talk to you soon.